Hello everyone, welcome to Uma's classroom. And today I thought I can be here to discuss an important topic for chemistry. This is especially for high school chemistry, or sometimes in college level chemistry there is a lot of discussion on this topic, that is atomic structure. And today I picked up a different model that I will go through the topic from the notes that I have, because I have seen many times my students, when they are studying from any book on their own, they are facing issues in understanding that topic. So that's why I have decided to go with the topic from certain materials and explain them step by step, and just would try to make you all understand that nowadays the situation is super crazy. So to become an independent learner, it is very important. That's why when you are studying a new topic on your own, how to go with it. I have picked up the chapter Atomic Structure, and this topic is academically very important because in most of the times high school chemistry curriculum includes this topic. Sometimes in college chemistry curriculum this topic is important, and I know many exams are there where chemistry require is the prior requirement, prior knowledge of certain topics of chemistry be should require. The atomic structure is one of the most important topic for that. So without extending any other discussion, I am directly going to the topic. Then the first thing that I would like to read aloud and explain time to time, that is Dalton's atomic theory. And every time I want the students to be seated with a pen and paper, if required, as they can make essential notes. And the utility of the video would be like that. Suppose if you don't like to read at a stretch, then just close your eyes and put your headphone on, and you can listen to this part to the video, and that will also be helpful to learn something, because always traditional learning, that doesn't give us comfort. And another thing I would like to mention, when you are facing any topic, you are trying to learn any topic on your own, especially new topic, please be seated with a small English to English dictionary, because we may come up with many terms that we are not very known to. So in that case, that will be helpful and will make our learning easier. So I am starting Dalton's atomic theory. This is the beginning of the atomic structure. Though you know that before the study of Dalton's atomic theory, you may get some stories of and the discussion of the structure of atoms that has started by cutting an aluminium foil, thin aluminium foil into half, then again cut it into pieces, again cut it into pieces, and keep cutting till you can cut the pieces. Now the question, how many small pieces you are supposed to get from that thin aluminium foil if you continuously keep cutting that one. And from many, at the beginning of the study, not only the chemists, many philosophers also, they were also included, like Democritus, Aristotle, they who couldn't imagine the exact number of small pieces of aluminium foil, but they have tried to give us some idea that maybe uncountable numbers of pieces can be taken out from that aluminium foil, but whatever it is, Dalton's atomic theory was the first attempt to discuss the atomic structure. John Dalton was born in England in 1766. He was a teacher who spent his spare time doing scientific experiments. Because of his interest in predicting the weather, Dalton studied the behavior of gases in air. This is interesting. Based on the way gases exert pressure, Dalton correctly concluded that a gas consists of individual particles. So, this is another side of Dalton's study. The next part, evidence for atoms. Dalton gathered evidence for the existence of atoms by measuring the masses of elements that combine when compounds form. He noticed that all compounds have something in common. No matter how large or small the sample, the ratio of the masses of the elements in the compound is always the same. In other words, compounds have a fixed composition. I already mentioned this topic is especially for high school students and college level students. So the terms you are getting like composition, elements, I hope you are pretty much aware of the definition of these terms. So I'm not going in detail. For example, when magnesium burns, combines with oxygen. This is a very popular example of chemical reaction. The product of this change is a white solid called magnesium oxide. A 100-gram sample of magnesium combines with 65.8 grams of oxygen. A 10-gram sample of magnesium combines with 6.58 grams of oxygen. The ratio of the mass of magnesium to the mass of oxygen is constant in magnesium oxide. So, this example is taken to make us all understand the composition of the constituent elements of any compound is always fixed. Now, the Dalton's atomic theory. Dalton developed a theory to explain why the elements in a compound always join in the same way. Now I believe it is clear to all of us that why the formation of magnesium oxide example is taken over here, because he developed a theory to explain why elements in a compound always join in the same way. He proposed the theory that all matter is made up of individual particles called atoms, which cannot be divided. And the main points of Dalton's theory are, so now I am going to read the main points of Dalton's theory, and I hope you all will have some notes on it. If you do not have, you can try to make a note on that point wise. So, point one, all elements are composed of atoms. All elements are composed of atoms. Point two, all atoms of the same element have the same mass. All atoms of the same element have the same mass. And atoms of the different elements have different masses. Atoms of the different elements have different masses. Now, point 3. Compounds contain atoms of more than one element. Compounds contain atoms of more than one element. And point 4. In a particular compound, atoms of different elements always combine in the same way. Point 4. In a particular compound, atoms of different elements always combine in the same way. And Dalton's he made some wooden spheres to represent the atoms of different elements. And surprisingly, those wooden spheres, the surface of the wooden spheres, that was different from each other. If he wanted to represent the atoms of the same element, he picked up the wooden spheres looks alike, and when he wanted to show the atoms from the different elements, he always picked up wooden spheres who were not looking alike. So he tried to make it so simple. He tried to keep his theory so simple. We can also try something, making some models of Dalton's atomic theory. Modeling in science and mathematics, this is very important. So if I want to make Dalton's atomic theory model, the easiest way that we can show the atoms of the same element, they look alike. So I would try to make two similar type of paper balls. He used wooden balls, we can try with paper balls. And we can use different colors, different sizes, different shapes, different surface structure just by using paper balls. And atoms from the different element to different types of paper balls. So whenever you are studying any theory or solving any problem, if you have some time, maybe in holidays, you can always try to model that. So once you are good in modeling, shaping that model, that means your understanding is perfect. In the model of atoms, based on Dalton's theory, the elements are pictured as solid spheres I just mentioned. Each type of atom is represented by a tiny solid sphere with a different mass. Recall that a theory must explain the data from many experiments. Because Dalton's atomic theory made that goal, the theory became widely accepted. Over time, scientists found that not all the Dalton's ideas about atoms were completely correct. But this did not cause later scientists to discard the atomic theory. Instead, they revised the theory to take into account new discoveries. So, this was the basement. Afterwards, the scientists they made corrections, they made new discoveries, but they couldn't discard Dalton's atomic theory. So, this was the beginning of atomic structure, where I have tried to given you some idea about Dalton's atomic theory, the points covered under Dalton's atomic theory. Somewhere you may get postulates of Dalton's atomic theory and try to model Dalton's atomic theory. How you can try for a science fair, I have already given some brief idea. And Next, I would like to switch on to the another discussion which has equally important role in the discussion of atomic structure. Though I know atomic structure means mainly Bohr's model, Rutherford model, electron cloud model. These are the most popular and very, very important structures and models under this topic. But before going to that, we are supposed to know the history of making those models, popular models. So, after Dalton's atomic theory, I would like to talk about Thompson's model of the atom. Thompson's model of the atom. And who all are watching me, if anyone confirms that you can hear me well, that would be nice. Then I would be able to understand that yes, my lessons or my goal is at least partially satisfied. It is helping you in any way. So, who all are watching, if you can send me some comments that you can hear me well, or if you want me to adjust the volume, it would be great. So, I am moving to the topic Thompson's model of the atom. When some materials are rubbed, they gain the ability to attract or repel other materials. Maybe in your middle school days, you have tried this experiment in physics. And there was a very popular experiment with hairbrush and paper pieces. I hope you all have tried that. Glass and the amber have the property. Based on their behavior, such materials are said to have either a positive or negative electric charge. Objects with like charges, they repel each other or push apart. Objects with opposite charges attract or pull together. Some charged particles can flow from one location to another. A flow of charged particles is called electric current. When you turn on an appliance such as a hairdryer, a current flows from the wall socket through the appliance. Joseph John Thomson, better known as J. Thomson, used an electric current to learn more about atoms. So, this is the beginning of his study. Now, I am coming to his experiment. Though I'm not drawing anything, I'm not showing any model, I'm not showing any picture of that, but still, I have a belief that from reading, you will also be able to understand. The purpose of this session is to make the students understand that sometimes you can learn something independently. Yes, if it's the first time, will have some hiccups and bumps, definitely. But if you want, you can overcome. And I repeat, in this situation, nowadays situation, this has become very important to become an independent learner. So I'm coming to Thompson's experiment. Thompson used a device like the, just let me see, I'm sorry, there was some typing error. So I would like to say it like that. Thompson used a device in which at the center is a sealed glass tube from which most of the air has been removed. So Thomson actually used a device. At the center of the device is sealed glass from which most of the air has been removed. So the middle part of the device, this is a sealed glass, and definitely from this kind of glass tube, and definitely from this glass tube most of the air is taken out, is removed. There is a metal disc at each end of the tube. So if this is the tube and this is totally almost empty, air free, this end is closed with a metal disc, the other end is also closed with a metal disc. So I can easily model it like that. Suppose this is the tube, this end is closed with a metal disc, the other end is also closed with another metal disc, and the middle part, that means the tube, from the tube most of the air has been taken out. So I have just used some plastic bottle to visualize the model. Whenever you are trying to learn something new, just try to use some handy objects to make your understanding better. Wires connect the metal. Wires connect the metal discs to a source of electric current. When the current is turned on, one disc becomes negatively charged and the other disc becomes positively charged. A glowing beam appears in the space between the discs. Thomson hypothesized that the beam was a stream of charged particles that interacted with the air in the tube and caused the air to glow. In one experiment Thomson did to test his hypothesis, he placed a pair of charged metal plates on either side of the glass tube. The plates caused the beam to deflect or bend from its straight path. Thomson observed that the beam was repelled by the negatively charged plate and attracted by the positively charged plate. So what he did actually, I repeat, Thomson used a sealed tube of gas in his experiment. When the current was on, the discs became charged and a glowing beam appeared in the tube. This is the first situation. Suppose tube A or situation A. Next, tube B or situation B. The beam bent toward a positively charged plate placed outside the tube. Now, what was the charge on the particle in the beam then? This is the question. This is the inference. And before going to Thompson's model, there I would like to read some passages which shows the evidence of subatomic particles. Thomson concluded that the particles in the beam had a negative charge because they were attracted to the positive plate. He hypothesized that the particles came from inside atoms. He had two pieces of evidence to support his hypothesis. No matter what metal Thomson used for the disk, the particles produced were identical. The particles had about 1 over 2000 the mass of a hydrogen atom that is the lightest atom. Thomson's discovery changed how scientists thought about atoms. Before his experiment, the accepted model of the atom was a solid ball of matter that could not be divided into smaller parts. Thomson's experiments provided the first evidence that atoms are made of even smaller particles. Thomson revised Dalton's model to account for these subatomic particles. This is the main importance of Thomson's atomic model. Now, then what is Thomson's model in brief? An atom is neutral, meaning it has neither a negative nor a positive charge. How can an atom contain negative particles and still be neutral? There must be some positive charge in the atom. In Thomson's model of the atom, the negative charges were evenly scattered throughout an atom filled with a positively charged mass of matter. The model is called Plum-pudding model after a traditional English dessert. You might prefer to think of Thompson's model as the chocolate chip ice cream model. Think of the chocolate chips as the negative particles and the vanilla ice cream as the positively charged mass of matter. So, one thing is very clear according to this model. The concept is that the positive charge is diffused or scattered as a mass of positive charge, and the negative charges are believed to be embedded into this positively charged mass. That's why it's easy to compare with a chocolate chip model. When the chocolate chips are spread evenly throughout the ice cream, their negative charges balance out the positive charge of the vanilla ice cream. So, this is another way. Try to pick up some examples from your surroundings that you can see, you can feel. This will make your learning easier. I think now Thompson's model, plum pudding model, has become little more easier for all of us to understand. A scoop of chocolate chip ice cream can represent Thomson's model of the atom. The chips represent negatively charged particles, whereas the vanilla ice cream represent the mass of positively charged matter, and the chips are sprayed evenly through a mass of positively charged matter. I repeat, that is the vanilla ice cream. So, this is Thomson's model, which was taken as the second attempt to discuss or to construct the structure of atoms. And always keep your eyes open whenever you are visiting any scientific lab, or when suppose you are visiting any science museum, any school, friend's place, any bookstore, wherever you go, if you see some model which is, or if you see some pictures or notes or sometimes quotations which you can correlate with your topic, please try to grab a picture of that. Always buying that poster or buying that model or visiting the place regularly, that may not be possible. I usually do that. Just simply in my mobile, I just try to grab some pictures. I can show you like that. For example, at this moment, I have this picture, models of atoms. Oh, sorry, one moment. Just like that. Here, my purpose is not to exactly show you the picture of these two different models, Dalton's atomic theory and Thompson's model of atomic structure. My purpose is that whenever possible, resources are available everywhere and it is very scattered. So if you can connect any picture or any poster from the places you visit, try to grab a picture. So maybe in the next time when you are opening the same topic, you can see, you can correlate that picture, you can use that picture for your understanding. So now I would like to switch on to the next part of our discussion of atomic structure, and that is Rutherford's atomic theory. And we all know the popularity of Rutherford's atomic theory, though this theory also uh, had some corrections, had some modifications, but in discussing or in learning the structure of an atom, all these theories, Dalton's atomic theory, Thompson's model, Rutherford's atomic theory, next Bohr's theory, and then finally electron cloud model, they all are in a row. We cannot neglect them. So, though I didn't receive any comment like that you cannot hear me or something like that, so I'm taking that it is going well. Now, Rutherford's atomic theory. When you try something new, you may have expectations about the outcome. Does the outcome always meet your expectations, or are you sometimes surprised? Scientists can also be surprised by the results of their experiments, but unexpected results can lead to important discoveries. This is what happened to Ernest Rutherford. So, these are the basic steps of any scientific experiment. First, hypothesis, then you have to gaze a result or inference of your experiment. And this inference, this is assumption, may be right, may be wrong. But this is the important step of scientific experiment. When you set up any experiment, you have to follow this step. And for Rutherford, he found something surprising which led him to discover something new. Let's see what is that. Rutherford's hypothesis. In 1899, Ernest Rutherford discovered that uranium emits fast moving particles that have a positive charge. He named them alpha particles. In 1909, Rutherford asked one of his students, to find out what happens to alpha particles when they pass through a thin sheet of gold. Recall that in Thompson's model of the atom, the mass and positive charge are evenly spread throughout an atom. Based on this model, Rutherford hypothesized that the mass and charge at any location in the gold would be too small to change the path of an alpha particle. He predicted that most particles would travel in a straight path from their source to a screen that lit up when struck. Those few that did not pass straight through would be deflected only slightly. So this is the hypothesis and proposed by Rutherford. And Rutherford gold leaf experiment or gold foil experiment is very historic and very famous. We need to study in detail, and many of you, I think you have already studied, so you have some prior knowledge. What is that one? For whom this is a new topic, I can assure this is not anything very, very difficult that you won't be able to understand. So let's start with that one. The gold foil experiment. Marsden, a student of Rutherford, used the equipment. He aimed a narrow beam of alpha particles at the gold. So, by using some instruments or equipment, a narrow beam of alpha particle was aimed at the gold. The screen around the gold was made of a material that produced a flash of light when struck by a fast-moving alpha particle. By observing the flash, Marsden could figure out the path of an alpha particle after it passed through the gold. Some of the locations of the flashes on the screen did not support Rutherford's prediction. Some of them supported, but some of them did not. More particles were deflected than he expected. About 1 out of every 20,000 was deflected by more than 90 degrees. Some of the alpha particles behave as though they had struck an object and bounced straight back. So if we critically observe this, it has three different parts, this experiment. First was the hypothesis. And the second part was the assumption of results, which is supposed to, and the third part, which was supposed to be supported by the experimental setup. And when I was talking about the steps of scientific experiment, I already mentioned your assumption, your prediction can be true, cannot be true. So this has happened with Rutherford also. It is clear from this paragraph or the passage that he got some of the results as expected, but most of the results which was not expected. And that unexpected result or surprise that surprised him and which led him to extend his work and to discover something new. Now we are moving to the next part, discovery of the nucleus. The alpha particles whose paths were deflected must have come close to another charged object. The closer they came, the greater the deflection was. But many alpha particles passed through the gold without being deflected. From these results, Rutherford concluded that the positive charge of an atom is not evenly spread throughout the atom. It is concentrated in a very small central area that Rutherford called the nucleus. The nucleus is a dense, positively charged mass located in the center of the atom. And the plural is nuclei. In many books or resource materials, you may get the word nuclei, that's also fine. Because Thompson's model no longer explained all the evidences, Rutherford proposed a new model. According to Rutherford's model, all of an atom's positive charge is concentrated in its nucleus. The alpha particles, whose paths were deflected by more than 90 degrees, came very close to a nucleus. The alpha particles whose paths were not bent moved through the space surrounding the nuclei without coming very close to the nucleus. The inside of an astrodome. Astrodome is actually a dome-shaped stadium. And the roof of the stadium can be rises approximately 200 feet above the center of the field. If an atom had the same volume as the stadium, its nucleus would have the volume of a marble. The total volume of an atom is about a trillion, that means 10 to the power 12 times the volume of its nucleus. So here also the example of this nuclear model is taken by citing the example of an astrodome. Astrodome is a dome-shaped stadium. And the roof of the stadium usually rises to a height of approximately 200 feet above the center of the field. And it is compared to the structure of atom according to Rutherford model. If an atom had the same volume as the stadium, its nucleus would have the volume of a marble. So this example is taken to make us understand that the volume of the nucleus compared to the volume of the entire atom is very small. The total volume of an atom is about a trillion, that is 10 to the power 12 times the volume of its nucleus. So I think this is precisely giving us a clear idea how big is the atom compared to its nucleus. Now, if you are planning to construct a model of the atom, please keep this in mind. And as this is very big, so please do some research work before constructing that model, that how you can keep the proportion of the nucleus and the atom. Size of the nucleus, or better to say volume of the nucleus and volume of the entire atom. When the existence of subatomic particles was understood, so it's better to discuss something or include something about some subatomic particles in our discussions. Beams like the ones Thompson produced create the images on many television screens. When a beam sweeps across the screen, spots on the screen light up in the same way the screen in the gold foil experiment lit up when struck by an alpha particle. In a color television, there are three beams, one for each primary color of light: red, green, and blue. The particles in these beams are considered as subatomic particles. Now, few properties of subatomic particles. By 1920, Rutherford had seen evidence for the existence of two subatomic particles and had predicted the existence of the third particle. Protons, electrons, and neutrons are subatomic particles. Protons. Based on experiments with elements other than gold, Rutherford concluded that the amount of positive charge varies among elements. Each nucleus must contain at least one particle with a positive charge. Rutherford called these particles protons. A proton is a positively charged subatomic particle that is found in the nucleus of an atom. Each proton is assigned a charge of plus 1. Some nuclei contain more than 100 protons. Next is electrons. The particles that Thompson detected were later named as electrons. Electrons comes from the Greek word meaning amber. An electron is a negatively charged subatomic particle that is found in the space outside the nucleus, and each electron has a charge of -1 or -1. Neutrons. In 1932, the English physicist James Chadwick designed an experiment to show that neutrons exist. Chadwick concluded that the particles he produced were neutral because a charged object did not deflect their paths. A neutron is a neutral subatomic particle that is found in the nucleus of an atom. It has a mass almost exactly equal to that of a proton. In most of the textbooks or resource materials, you will get a chart where properties of subatomic particles are compared. And there you will get their symbol, their relative charge, relative mass, actual mass, and sometimes some model representation in different colors. Electrons represented by yellow colored balls, protons represented by green colored balls, and neutrons represented by red colored balls. And if you did not notice already, now onwards you can start looking for these three colors when switching on a television. Now, comparing subatomic particles, I just mentioned that in most of the textbooks you will get a comparison chart. If you do not get just from my discussion, you can make a comparison chart. And relative mass of electron, this is Proton's mass is taken as 1, neutron's mass is taken as 1. So electron's mass is taken as 1 over 1836. Actual mass in gram for electron, it is 9.11 times 10 to the power negative 28 gram. For proton, it is 1.674 times 10 to the power negative 24. And for neutron, it is 1.675 times 10 to the power negative 24. So mass-wise, figure-wise, mass of proton and neutron, this is almost same, almost equal. And the symbol of electron is small e with a negative sign. For proton, it's a small p with a positive sign overhead, right, top right corner of p. And for neutron, it is just small n. Relative charge for electron, it is -1, usually written as 1 minus. Proton 1 plus. Neutron 0. So this is a brief comparison of all three subatomic particles, and there are few important definitions related to the same topic, that is atomic number and mass number, because these two definitions are closely connected to the number of protons, number of electrons, number of neutrons. So let's go over atomic number. The atoms of any given element always have the same number of protons. For example, there is one proton in the nucleus of each and every hydrogen atom. Therefore, hydrogen is assigned the atomic number 1. The atomic number of an element equals the number of protons in an atom of that element. Hydrogen atoms are the only atoms with single proton. Atoms of different elements have different numbers of the protons. The sulfur is assigned with atomic number 16 because the sulfur atom has 16 protons. You can use atomic numbers to refer to elements like names and symbols because each element has a unique atomic number. Each positive charge in an atom is balanced by a negative charge because atoms are electrically neutral. So the atomic number of an element also equals the number of electrons in an atom. Each hydrogen atom has 1 electron. Each sulfur atom has 16. Next definition is mass number. The atomic number tells you the number of protons in an atom's nucleus. It does not give you any information about the number of neutrons in an atom. For that information, you need to know the atom's mass number. The mass number of an atom is the sum of the protons and neutrons in the nucleus of that atom. An atom of aluminium with 13 protons and 14 neutrons has a mass number of 27. 13 plus 14, 27. If you know the atomic number and the mass number of an atom, you can find the number of neutrons by subtracting. So simple formula, number of neutrons equals mass number minus atomic number. Number of neutrons equals mass number minus atomic numbers. So you may get one fill in the blank type questions from this discussion, suppose atomic number is provided, you are supposed to predict the number of protons, number of electrons, or with some other information is provided, how can you gauge the number of neutrons present over there? And the very closely related part to this topic is the study of periodic table, though we are not talking about that over here. Just another definition I have to discuss over here, that is the definition of isotopes. In Dalton's atomic theory, all the atoms of a given element are identical. Every atom of a given element does have the same number of protons and electrons, but every atom of a given element does not have the same number of neutrons. Isotopes are atoms of the same element that have different number of neutrons and so different mass numbers. Isotopes of an element have the same atomic number but different mass numbers because they have different number of neutrons. Their number of protons are same but number of neutrons are different. So their atomic numbers are same but mass numbers are different. For example, every atom of oxygen has 8 protons. Some oxygen atoms have 8 neutrons and a mass number of 16. Some oxygen atoms have 9 neutrons and a mass number of 17. Some oxygen atoms have 10 neutrons with a mass number of 18. When it is important to distinguish one oxygen isotope from another, the isotopes are referred to as oxygen 16, oxygen 17, and oxygen 18. All three oxygen isotopes can react with hydrogen to form water or combine with iron to form rust. The purpose of taking these examples is that isotopes are all isotopes, they behave equally in a chemical reaction. So there is no change in properties, there is only change in number of neutrons. With most elements, it is hard to notice any differences in the physical or chemical properties of their isotopes. Hydrogen is an exception. Hydrogen 1 has no neutrons. Almost all hydrogen is hydrogen 1. Hydrogen 2 has 1 neutron and hydrogen 3 has 2 neutrons. Because a hydrogen 1 atom has only 1 proton, adding a neutron doubles its mass. Water that water that contains hydrogen 2 atoms in place of hydrogen 1 is called heavy water. And physical properties, if we compare the physical properties of ordinary water and heavy water, there is a difference. So this is the exception. For ordinary water, the melting point is 0 degree Celsius, whereas for heavy water, the melting point is 3.81 degrees Celsius. For ordinary water, boiling point is 100 degrees Celsius, whereas for heavy water, the boiling point is 101.42 degrees Celsius. And density of ordinary water is 0.99701 gram per centimeter cube, whereas the density of heavy water is 1.1044 gram per centimeter cube. So this is the exception and few properties, that's why I mentioned over here. Otherwise, almost all the isotopes, it is very hard to distinguish in between isotopes. They reflect same type of physical and chemical properties. I repeat, in most of the cases, one exception I found as an example, so I cited it over here. And now it's time to stop because we have already discussed three important models of atomic structure. We started from Dalton's atomic theory, then switched to Thompson's model, and then finally we came to Rutherford model. And for Rutherford model also, I pictured one when I visited some library, and it looks like this. Oh, sorry. And whenever possible, you also try to grab some pictures, try to draw some pictures, as it makes your understanding easier. And if you are really benefited from this session, don't forget to let me know. Share this video among your friends, teachers, or anyone who is interested to learn about atomic structure. And as I covered many topics, I hope the passages I read out will help you to cover many question answers. Still, if you feel you need some discussion of question answers, please let me know. I will always try to help you. So I think that's enough for today. Wish to see you all over here soon. Thank you so much.